If you think about it, classification means asking a simple question: which label fits this whole signal? The catch is that the answer often depends on short pieces, not the entire curve. Many large models learn trends for prediction, but they miss these short clues. This work asks, can we pre-train one model that learns such useful pieces across many datasets, then reuse them for new tasks without starting over? This figure shows the core idea visually. Time series from very different domains are all fed into one shared model. The red segments are shapelets, short parts of the signal that matter for deciding the class. The key point is that these shapes appear in many domains even if the signals look different. By learning these shapes jointly, the model avoids being tied to one dataset and gains reuse across tasks. So how does this work? We start with one signal and cut it into overlapping pieces of different lengths. Each piece is encoded using simple operations that capture level and change. These become shape tokens. An attention step then asks the question, which pieces matter most? Those are summed into a class token. This is done first for long windows, then refined with shorter ones. One shared adapter does all this, which keeps learning efficient and consistent. Here you can see the full pipeline. The adapter turns raw subsequences into tokens. Both shape tokens and class tokens then pass through a transformer. Prototypes act like class anchors in feature space. During training, tokens are pulled closer to their class prototype and pushed away from others. This happens at two levels: whole samples and individual shapes. The idea is simple: good classes form tight, well-separated groups. The experiments ask one main question: does this extra structure help in practice? Unsurprisingly, the answer is yes. Otherwise, there would have been no point to making this video. After pre-training on many datasets, the model is fine-tuned on new ones and consistently scores higher than strong baselines. Even when few labels are used during pre-training, results stay strong. In zero-shot tests, where no fine-tuning is allowed, the learned features still separate classes well. This figure highlights why attention matters. Red regions mark parts of the signal the model relies on most. For ECG data, it focuses on known waveform sections used by experts. For motion data, it highlights key movement intervals. The important point is that these highlighted parts align with known class cues. This shows the model is not guessing blindly. It uses clear local signal evidence to decide. To wrap up, the paper takes classification seriously instead of borrowing tools meant for prediction. By building shape awareness into pre-training, the model learns signal parts that matter across tasks. Prototypes keep class structure clear, even with few labels. The result is a model that transfers well, performs strongly, and gives insight into its decisions. It is a practical step toward general-purpose time series classifiers.